Hello everyone, now I'm going to give you a quick demonstration of the question 1 in assignment 6. The question asks us to consider a quadrilateral four-load isoparametric four-integration element with the coordinates of load 1, 0, 0, and load 2, 5, 0, and load 3, 5, 5, and load 4, 0, 5. And it's in meter. And the assumed Young's modulus is 20 G/par and Poisson's ratio is 0.2. And the first part, the question asks us to compare the stiffness matrix for the plane string condition obtained manually with the one obtained using ABAQUS. So for about how to export stiffness matrix from ABAQUS, I have demonstrated this in our previous video. And in that video, I mentioned I talked about how to export stiffness matrix using two methods, and you can refer to that video if you forgot how to export stiffness matrix. And for the second part, so assume that load 1 and load 2 to be fixed, and find the displacements of load 3 and load 4 under a vertical gravity load. If the density of the material is equal to 2,400 kg per meter cubed and the gravity load is 9.81 Newton per kilogram. So the question asks us to find the stress and strains at the integration points of the element. So when we use full integration instead of using reduced integration. So we need to compare stress and strain obtained by hand calculation to the values obtained from ABAQUS. So now let's get started. So first part, we need to create a part, and it's a 2D plane string state, right? So we need to create a part, 2D part first. And the maximum length of the edge is 5, so we can put 10 here and click continue. So you can click, if you take a look at this question, you know this is a square. So just for the future reference, if you want to create a quadrilateral element without right angles, so you can just use this one. So click the first point is 0, 0, and then the next point is 5, 0. Then the next point is 5, 5. Then next point is 0, 5. And then we need to close this geometry. So click this point, and then hit middlemost button and click down. Now we have this geometry. And then next part, we need to create a material property. So let's use the default limb, and it's a elastic material, so we click elastic. So since for the coordinate we use the meter, so for the Young's modulus we need to use the par. This is based on the consistency unit. So we put 20 G/par is 20 followed by 9 zeros. And the Poisson's ratio is 0.2. Yeah. And then we also need to assign a density for this material. So we click go to the general, click density, and then we put 2,400 as the density. Click OK. Now we need to create a section, and we just use the material we just created and click OK. Then we assign this assign the cross section to this part and click done. we only have one section. So we use the default one and click OK. Now we need to mesh this part. So you can use what I demonstrated before by putting a seed on each edge, or you can just give a very big approximate global size. The maximum length of the edge is 5, so you can give 5, you can give 6, or you can give 10. Then the software will mesh this part using one element. So click apply and click OK. Now we have 4 seeds at the corners, and then click mesh, click yes. Now we have one element, and then we need to select the material, the element tab, and click done. So the question asks us to use a plain string and for integration. So we click OK. Now we have the material property and mesh, so we need to create an instance. So we click go to the assembly module and click this and part. So you can just you just need to click OK. So sometimes if you click apply and click OK again, then you will find you have 2 instances. So just click OK. Then you can check here, you only have 1 instance. So now next part we need to create a step. So we are going to perform a static analysis, use the default lane. So click continue. So here you can use nonlinear geometry because it will be small deformation, or you can just turn it on. It will not affect your results. So if you recall what we discussed in the lecture, you know that if you always keep it on, even when you have a large deformation, your result will be accurate. So for default, I like to put it on. So from now on, you can just put it on. And we talked about how the software will solve this problem. So here you can see that the solution technique, we are going to use the 4 Newton Raphson method. And sometimes we need to use quasi-Newton. But for now, you can just use the default one and click OK. So another thing that I like to mention is here. So you can change the increment size. This is the initial increment size, and this is the maximum and the minimum increment size. And now click OK. So for linear problem, you can just use the default option. For highly nonlinear problem, you might need to play with this option. I'll tell you more about it later on. Let's click OK. And then we have a step here. So let's apply boundary conditions and load. So based on the question, load 1 and load 2 will be fixed. Load 1 is 0, 0, load 2 is 5, 0. So let's click encapsulate boundary condition, click continue, and select this and this. So you need to hit shift, if you want to select 2 points. Okay, now we select these 2 nodes and click down and click encapsulate. Now we fixed this load 1 and load 2. And for the node, we need to apply a gravity load. So we go to the mechanical and go to the gravity and click continue. The load will be applied in step 1. Okay, click continue, and it's equal to 9.81. So it's going downwards. So we just need to put component 2 negative 9.81 and click OK. So you can see the gravity load is applied in this entire space. Now we just need to create a job, and let's call it question 1 from assignment 6. So click continue and click OK. Let's submit the job. Now the job has completed, so we can check the results. So this is the deformation. So if you want to check the displacement, so you can go to the tools, load, and pro values. So we go to the load and we check the displacement here. So it's here you can see it's 1 meter stress. So let's just find the displacement. You can see this is our displacement, and this is the displacement. So it's the displacement is the seam over the entire field. So you can see, because it's gravity load, you can see this load is load 1 in this element. So when we define this load, we call load 1 is 0, 0. But in this in the software, load 1 is this point, load 2 is this point, and load 3 is this point. So load 4 is this point. So this is load 2. This is load 3. So this is 1, 2, 3, and 4. So this is very important because the load numbering order may be different from what you defined here. So you need to double check if which one is the load 1 in the software, so that you can compare your results accurately. So the question asks us to check the stress and strains at integration points. So we go to stress and strain. For example, if we want to check S11, then we go to the tools query. So we have this panel, and then we go to element prop values. So if you switch it to elements, you can see here we have a few options. The first one is integration points. So if you click this one, you will have and click this. So you will have S11. So this the first value, lactive 415, is associated with load 1. This is the load 1, so the integration point is here. And the second value is lactive 5780. It's associated with load 2. So I think load 2 is here. So, and then load 3 is here. So you have lactive 415. So you can see this value is at this integration point, and this value is at this integration point, because this is our load 1 and this is our load 3. It makes sense, right? Because the value is the same. And also, if you want to check the value at the centroid, so you can click here. So you will export your S11 at this centroid. And similarly, if you want to check the stress and strain at these 4 colors, so you can just click to element nodal. Click here. You will have stresses from these colors. So this is from the first node. This is the second node. This is the stress associated at the fourth node. This is the stress associated with the third node. And the last one is element phase. I think it will give you an average stress over this element. So because this is the stress is linearly changed, you can write down this value, and when you click centroid, it will give you the same, exactly the same value. Okay, then you can compare the value at the integration point with your hand calculation.